We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. We're looking at Neptune's orbit, and it's not following Newton's laws. This is hard to believe. The closest images ever taken of Neptune revealed a shocking discovery. For ages, Neptune has captivated scientists and dreamers with its mysterious charm, hidden behind a veil of secrecy and passion. However, due to tireless efforts in scientific discovery, scientists are on the verge of a remarkable breakthrough. The clearest pictures ever taken of this faraway icy giant. These images provide a peek into Neptune's stormy atmosphere, revealing a surprising finding that will change how people see the outer edges of the solar system forever. In August of 1977, Voyager 2 embarked on an extraordinary journey through our solar system, venturing where no spacecraft had gone before. It set out to explore the outer reaches of the celestial neighborhood, marking a remarkable moment in space exploration. After a 12-year journey, Voyager 2 reached Neptune in 1989. As it approached the distant ice giant, it captured breathtaking footage that unveiled a majestic world shrouded in stirring bands of azure clouds. Imagine witnessing this distant sibling of Jupiter adorned in shades of mesmerizing blue. Among Neptune's mysterious features, Voyager 2 detected a colossal storm raging across its atmosphere, resembling a massive slate-colored uproar. Additionally, the spacecraft discovered 4 mysterious rings encircling the planet, along with 6 previously unknown moons, adding to the allure of this distant realm. Despite its epic voyage spanning 7.1 billion kilometers, Voyager 2's encounter with Neptune was fleeting, lasting only a few hours. However, this brief rendezvous provided humanity with unprecedented views of the distant ice giant, capturing the essence of Neptune's captivating beauty. When considering Neptune, many of us think of the iconic image memorialized by Voyager 2, a portrait showcasing the planet's tower white clouds and turbulent storms all bathed in a famous yet mistaken hue of blue. In reality, Neptune's true color is a softer, lighter shade of greenish blue, a subtle detail often overlooked in the grandeur of space exploration. When venturing online in search of more snapshots of Neptune, people quickly notice a scarcity of images. Despite Voyager 2's impressive feat of flying within a hair's breadth of just 4,500 kilometers from Neptune's surface, the number of available photos remains surprisingly low. What makes Neptune so elusive to capture on camera? Imagine that Neptune resides a staggering 30 times farther from the Sun than Earth. This vast distance means that it receives only a fraction of the sunlight that our planet enjoys. Consequently, when Voyager 2 finally caught up with Neptune after its gravity-assisted journey past other outer planets, it was hurtling through space at an astonishing speed of 27 kilometers per second. While Neptune may seem like a distant speck in the universe, its allure lies in its perplexing blue hue and mysterious atmosphere. But capturing these mesmerizing details proved to be quite the challenge for Voyager 2. With Neptune receiving only a mere 0.1% of the sunlight that reaches Earth, the spacecraft struggled to snap clear, non-blurry photos amidst the dimly lit expanse. Voyager 2's ingenuity knew no bounds. By deftly working its thrusters to swing as it soared past and employing extended exposure techniques, the spacecraft managed to capture and transmit back to Earth some of the closest and most mesmerizing images ever taken of Neptune. Just a couple of hours before Voyager 2 zoomed past Neptune, it captured an incredibly detailed picture in which scientists got a close-up view of some interesting features high up in the planet's atmosphere. Long, wispy clouds that resemble the cirrus clouds people see on Earth were not made of water vapor like Earth's clouds. These clouds are crafted from frozen methane, giving them a surreal appearance. Imagine these cloud formations stretching for thousands of kilometers running parallel to Neptune's equator. They are not just some puny clouds either. Each streak measures between 50 to 200 kilometers wide. These clouds are so high up that they cast shadows onto the hazy layer about 50 kilometers below. What's even more mind-blowing is that even though Voyager 2 had already checked out all the other gas giants before Neptune, it wasn't until Neptune that we got our first ever glimpse of these elusive cloud shadows, as evidenced by the grainy image captured. These high-altitude clouds are like fleeting guests in Neptune's atmosphere, always on the move and changing shape. Recent observations from the Hubble Space Telescope revealed that these clouds can form and disappear in the blink of an eye, showcasing the dynamic nature of Neptune's weather patterns. When this picture was captured, strong winds would have been swirling around the ice giant, some blowing as fast as 1,000 kilometers per hour. That's 3 times quicker than winds on Jupiter and almost 9 times speedier than those on Earth. Voyager 2 revealed that Neptune experiences some of the most extreme weather in the solar system, and when the spacecraft flew by, it encountered a striking example of this event. This image is the closest view ever captured of the once furious storm known as the Great Dark Spot, a large oval-shaped cyclone resembling Jupiter's Great Red Spot. This immense weather system was roughly the size of the entire Earth. What's fascinating about this image is that the center of the storm appears to be relatively clear of clouds, forming a vast dark void slicing through Neptune's atmosphere. Neptune is an incredible ice giant, about 4 times wider than Earth. Its radius is around 15,300 kilometers, and it has an enormous volume of 15 trillion cubic miles. To put that in perspective, Neptune is 58 times larger in volume than Earth. This fascinating planet is mostly made of water, methane, and ammonia. Unlike Earth, Neptune doesn't have a solid surface. Instead, its thick atmosphere extends deep into the planet, reaching down to a mantle made of methane and ammonia ice surrounding a rocky core. Interestingly, scientists think that Neptune might even have a superhot ocean hidden deep inside. Despite its icy name and outer appearance, the conditions inside Neptune are anything but cold. But how can a planet sustain such an ocean when it is so far from the sun? Sunlight takes a whopping 4 hours to reach Neptune's massive surface. Neptune is incredibly cold, with an average atmospheric temperature of -360 degrees Fahrenheit, making it one of the chilliest places in the solar system. Interestingly, most of Neptune cooled down between 2003 and 2018, though there was some warming near the South Pole from 2018 to 2020, likely due to seasonal changes in the atmosphere's chemistry. The mystery of how an ocean might form inside this icy giant remains unsolved. However, scientists have some theories. One idea is that internal heating caused by gravitational compression or interaction between Neptune and its largest moon Triton might play a role. Yet not all researchers agree. For instance, scientists Sloan Viktorovic and Andrew Enoll argue that the chances of oceans forming on Neptune due to its internal heat are quite slim, estimating it at only 15%. Right now, their calculations suggest that it might take 1 billion years for the probability of such an ocean to rise to 40%, assuming the giant continues to cool down over time. One interesting theory for Neptune's immense internal energy is that it might have collided with a cosmic object long ago. Neptune stands out as the only planet that radiates nearly 3 times more energy than it absorbs from the sun. This unusual energy output might be linked to the planet's significant 28-degree tilt on its axis, which is quite similar to Earth's tilt. This tilt means Neptune experiences seasons much like Earth does, but with a twist. Each season on Neptune lasts around 40 years. To put it in perspective, 1 Neptune year equals 165 Earth years, but a day on Neptune is just 16 hours long. This fast rotation generates extremely strong winds. Neptune's atmosphere is composed mostly of hydrogen, making up 80%, with helium accounting for 19%, and a small fraction, about 1%, of other gases including methane. The striking blue color of Neptune is a result of methane clouds in the upper atmosphere, which absorb red light and reflect blue. Methane plays a significant role in shaping the atmospheres of both Neptune and Uranus. Despite being the farthest planets from the Sun in our solar system, these ice giants still receive a significant amount of solar radiation, albeit much less intense than what planets like Earth receive. Neptune's vivid blue coloration has captivated astronomers for centuries, but the exact mechanisms behind its striking color continue to interest scientists. One fascinating aspect is the presence of high-altitude clouds composed primarily of methane ice crystals. These clouds scatter sunlight in a way that enhances the blue coloration, similar to how Earth's atmosphere scatters sunlight to create blue skies. Furthermore, Neptune's dynamic atmosphere exhibits a multitude of features, including massive storms and powerful winds. On the other hand, Uranus presents a different aesthetic with its muted pale blue color. This planet's unique tilt, where its axis is nearly parallel to its orbital plane, results in extreme seasonal variations. During its long polar winters, Uranus experiences prolonged periods of darkness, hindering the formation of high-altitude methane clouds that contribute to its overall coloration. In addition to methane, both planets' atmospheres contain trace amounts of other gases including hydrogen, helium, and ammonia. These gases, along with the intricate interplay of temperature, pressure, and atmospheric dynamics, create a complex and dynamic environment worthy of scientific exploration. Neptune holds many mysteries within its icy depths. Its intense blue coloration, derived from methane in its atmosphere, adds to its allure. But beyond its captivating hue lies a world of extremes. The storms that rage across Neptune's surface are not just any storms. They are colossal tempests, some spanning thousands of kilometers. These atmospheric disturbances, marked by dark and white patches, are the result of Neptune's rapid rotation, completing a day in just under 16 hours. This rapid spin generates intense wind currents, contributing to the planet's tumultuous weather patterns. Neptune's complex and dynamic atmosphere remains a subject of fascination, with ongoing research shedding light on its mysteries. As we continue to explore and analyze the data from past and future missions, Neptune's secrets may gradually unveil themselves, offering deeper insights into the outer reaches of our solar system. Neptune, the eighth and farthest planet from the Sun, is a subject of immense interest due to its unique characteristics and distant location. One of the most intriguing aspects of Neptune is its magnetic field, which is both unusual and complex. Unlike the magnetic fields of other planets in the solar system, Neptune's magnetic field is tilted at an angle of about 47 degrees from its rotational axis and is offset from the planet's center. This tilt and offset are believed to be the result of a combination of factors, including the planet's internal dynamo and the influence of its icy and rocky composition. The interaction of Neptune's magnetic field with the solar wind creates a dynamic magnetosphere that extends far beyond the planet itself, forming a protective shield against cosmic radiation. Neptune's moon Triton is another fascinating object of study. Triton is one of the largest moons in the solar system and is notable for its retrograde orbit, meaning it orbits Neptune in the opposite direction of the planet's rotation. This retrograde motion suggests that Triton was likely captured by Neptune's gravity rather than forming in place. Triton's surface is a mix of icy plains, rugged terrains, and active geysers that spout nitrogen gas into space. These geysers are driven by seasonal changes and internal heat, making Triton one of the most geologically active moons in the solar system. The presence of these geysers indicates that Triton might have a subsurface ocean, potentially enhancing its value as a site for future exploration. Another noteworthy moon of Neptune is Nereid, which has an eccentric orbit that varies significantly in distance from Neptune. Nereid's highly elliptical orbit suggests that its formation was influenced by gravitational interactions with other celestial bodies or perhaps by past collisions. The varying distance of Nereid from Neptune results in significant changes in its orbital speed and its gravitational interaction with the planet, making it an interesting subject for studying the dynamics of satellite orbits around distant planets. Neptune's rings, while not as prominent as those of Saturn, are still a significant feature. These rings are composed primarily of dark, microscopic particles and are less dense than those of Saturn. The rings are named after astronomers who contributed to the study of Neptune: the Adams, Leverrier, and Gall rings. The discovery of these rings provided important insights into the planet's gravitational effects and the dynamics of ring systems around distant planets. Observations of these rings suggest that they are relatively young and may be continuously replenished by dust and debris from Neptune's moons. The study of Neptune's weather patterns reveals a planet with extreme meteorological phenomena. The planet's atmospheric dynamics include the formation of large, dark storms and high-speed winds that create a turbulent environment. In addition to the Great Dark Spot mentioned earlier, Neptune also experiences smaller storm systems that can develop rapidly and dissipate within a short period. These transient storms contribute to the planet's complex weather system, which is influenced by factors such as seasonal changes and internal heat. Recent observations from the James Webb Space Telescope, JWST, have provided new insights into Neptune's atmospheric composition and dynamics. The JWST's advanced instruments have enabled scientists to analyze the chemical composition of Neptune's atmosphere with unprecedented precision. These observations have revealed the presence of various gases, including hydrogen sulfide, which contributes to the planet's unique color. Additionally, the JWST has detected the presence of auroras in Neptune's atmosphere, which are created by the interaction of the planet's magnetic field with charged particles from the solar wind. Neptune's orbit around the Sun is highly elliptical, causing significant variations in its distance from Earth and other planets. This elliptical orbit results in a wide range of temperatures and seasonal changes, which influence the planet's atmospheric and surface conditions. The extreme tilt of Neptune's axis also leads to significant seasonal variations, with each pole experiencing prolonged periods of darkness or sunlight depending on the planet's position in its orbit. The study of Neptune's atmosphere has also revealed the presence of complex cloud formations and atmospheric layers. These clouds, composed primarily of methane and other gases, play a crucial role in the planet's weather patterns and climate. The interaction of these clouds with the planet's magnetic field and solar radiation creates a dynamic and ever-changing atmosphere. Understanding these cloud formations and their impact on Neptune's climate is an ongoing area of research. Neptune's extreme distance from the Sun means that its energy sources are limited compared to planets closer to the Sun. Despite this, the planet exhibits a significant amount of internal heat, which contributes to its atmospheric dynamics and weather patterns. The source of this internal heat is not fully understood, but it is thought to be related to gravitational compression, tidal forces from its moons, and possibly radioactive decay. This internal heat helps to drive the planet's atmospheric circulation and contributes to the formation of its weather systems. In addition to its atmospheric and magnetic properties, Neptune's exploration has provided valuable insights into the formation and evolution of planetary systems. The study of Neptune's composition, rings, and moons has helped scientists to understand the processes that shape the outer planets and their satellites. This research has implications for our understanding of the formation of planetary systems beyond our own and provides valuable information for future exploration missions. As our technology advances and our understanding of Neptune deepens, future missions may reveal even more about this enigmatic planet. The development of new spacecraft and observational tools will enable scientists to explore Neptune in greater detail and uncover new mysteries about its atmosphere, magnetic field, and moons. The continued study of Neptune and its complex system will contribute to our broader understanding of the outer reaches of our solar system and the formation of planetary systems in the universe.